In the last section, we talked about permutations. That was a selection of objects where the order mattered. So, for example, this might be license plate numbers, where you've got the license plate ABC 123, and even though it's got the same letters and numbers, it's completely different than the license plate CBA 321. Well, today we're going to talk about combinations. Combinations, those are selections of objects where the order doesn't matter. So examples of this might be playing a card game and getting a hand of 5 cards. Let's say that you're playing poker and you've got the 5 cards, 10, Jack, Queen, King, Ace. Those are dealt to you in that order. Well, it's the exact same thing as if they were dealt to you as Ace, King, Queen, Jack, 10. Both of them are the same straight. So it doesn't matter what order you receive the cards, as long as you've got all of those cards, you've got the same hand, one way or the other. So a combination is a selection of objects from a group in which the order of items selected is unimportant. For example, say you are looking at the letters A, B, C, and D, and you just want to choose 3 of those 4. Well, if the order doesn't matter, you could have ABC, ABD, ACD, or BCD. Those are the different combinations. Compare this to permutations, which we talked about last time, where the order does matter. If the order does matter, then all of a sudden, instead of just these 4 combinations, you're going to be dealing with 24 permutations. So it's quite a difference. Here we'll use the following. Choosing R objects from a total of n without repetition. Order does not matter. We've got NCR equals n factorial over r factorial, n minus r factorial. So the difference in formula here between this and the permutation is having this r factorial in the bottom. Let's do some examples. Find the number of ways to select 3 letters from 4 without repetition. The order does not matter. Okay, so if I've got 4 letters total, that's going to be n equals 4. C, I'm choosing 3 of them. So this will be 4C3. Following this formula, I've got 4 factorial over 3 factorial, and then 4 minus 3 factorial. Well, this is 4 factorial over 3 factorial, 1 factorial, which is 4 times 3 times 2 times 1 on top. The bottom part, I've got 3 times 2 times 1, and then times another 1, this 1 factorial. Let's divide out what we can. 3s, 2s, one of these 1s, and we see, just as we saw earlier, we've got 4 over 1 or 4 left. So there are 4 ways to choose 3 letters from 4 without repetition. Okay, here's a common thing that we see. A lot of restaurants have an appetizer sampler where you can choose a whole bunch of appetizers, you can order them individually, or you might be able to save a little bit of money if they do have this appetizer sampler where you can order 3 of them for maybe the price of 2. So there are 8 appetizers at this restaurant, and you want to choose 3 of them. Now, the order in which you tell your server shouldn't matter whether you order, boneless wings, mozzarella sticks, and nachos. Okay, let's say that you want to go with those 3. It's the exact same thing as if you said mozzarella sticks, nachos, boneless wings. As long as that order gets put into the kitchen and your food comes to the table, it's not going to matter which way you say it. So let's find out, of 8 appetizers, how many ways can we choose 3 of them without repetition, because we don't want to do 2 orders of the same thing, without the order mattering here. So that'll be 8 objects in total, 8 appetizers. and I'm going to choose 3 of them. Okay, so this will be 8 factorial over 3 factorial, and then 8 minus 3 factorial. So I've got 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. That'll be the 3 factorial. And then 8 minus 3 factorial, that'll be 5 factorial. So I'll also have 5 times 4 times 3 times 2 times 1. Well, let's divide some things out. 5s, 4s, 3s, 2s, and 1s. And actually, I could have saved myself a little bit of time. For the top part, I could have done 8 times 7 times 6 times 5 factorial, since 5 factorial would have given me the 5, 4, 3, 2, 1, just like having the 5 factorial on the bottom. So I could have just crossed out those 5 factorials rather than writing each these out and then dividing them out each. All right, so what am I left with? Let's see, 8 times 7 times 6, and we'll divide by 3 times 2 times 1. So this will be 56. There are 56 different ways to choose 3 appetizers out of your 8. Which is probably why when you go to the restaurant, if there is an appetizer sampler, they would have a page where you should say choose 3 out of the 8 rather than writing out every single combination for people coming to eat. It would take up quite a bit of room, I'd imagine. All right, the next one says you enter a raffle. There are 40 people that have entered total. 3 people will win prizes. Here we'll assume that all the prizes are the same because the order does not matter, it says later. Find the number of ways to select 3 winners from 40 without repetition. Okay, for this one, we definitely want to employ that trick that we said. First, let's set it up. 40 people enter, choosing 3 of them to win. So this is 40 factorial over 3 factorial, and then 40 minus 3 factorial. So I've got 40 factorial over 3 factorial, 37 factorial. And that trick that I referred to is taking the top part and saying 40 times 39 times 38, and then times 37 factorial, instead of going all the way down to 1. Because on the bottom, I'm just going to do 3 times 2 times 1 times 37 factorial, and then I'll be able to divide these 37 factorials out. So what's remaining? I've got, do parentheses for the top here, 40 times 39 times 38. And I'm dividing by 3 times 2 times 1. So there are 9,880 different ways to select 3 winners from 40. All right, finding a probability using combinations. So you may recall from previous lessons that probability is the number of ways to satisfy an event over the total number of possibilities. So when I look at number 1 of this section, there are 4 boys and 8 girls on the debate team. The coach must select 3 students to attend the next meet. Doesn't look like there's any restrictions there so far. But then what is the probability that the coach will select all girls to attend the next meet? Okay, so there are 2 parts we have to find. The first part is the number of ways to satisfy the event. To satisfy the event, we need to pick 3 students that are all girls. Okay, so we need 3 of 8 students, girls. And we need to do this over the total number of ways to do this is 3 out of a total of 12 students, because 8 girls and then 4 boys. Okay, to pick 3 of 8 girls, this means of the 8 girls, I'm going to choose 3 of them. Technically, I could also say, let's multiply this by of the 4 boys, I want to choose 0 of them. I don't need to write that out in this case because no matter how many boys I've got, choosing 0 of them, there's only one way to do that, to choose none of them. So really, if I did that, I'd be multiplying by 1 anyway. So 8 choose 3. Let's do this first. This is 8 factorial over 3 factorial, and then 8 minus 3 is 5, so 5 factorial. All right, let's use the calculator for this time. I like to do a parentheses around the top and parentheses separately around the bottom. So I've got 8, go to your probability, factorial there, divide that by parentheses for the bottom. I'm going to do 3 factorial, and then 5 factorial. So the top part, this is 56. There are 56 ways to choose 3 of 8 girls to go to this meet. All right, now the total number of ways to choose 3 students out of 12 is 12C3. In this case, we'd have 12 factorial over 3 factorial, and then 12 minus 3 would be 9 factorial. So let's do that same thing. Let's do parentheses 12, and then factorial. Close that off, divided by parentheses. I've got 3 factorial, and then 9 factorial. This is 220. Therefore, the probability that the coach will select 3 girls the next meet, this is 56 over 220. We could reduce that. I want to find out what that is as a decimal. Oop, that's 55. I need to do 56. .2545. So it's a little better than 25%. How I find that is just moving this decimal over 2 spots, and that would be your percent chance. All right, for the next problem, there are 52 cards in a standard deck of cards. There are 13 cards in each suit: clubs, diamonds, hearts, spades. What is the probability that 5 randomly drawn cards, so you just take 5 cards face down, and then you look at them, without repetition, are all diamonds? So what are the chances you get all diamonds? So what we would need is the number of ways to get 5 diamonds over the total number of possibilities. I'll say possible hands. So the number of ways to get 5 diamonds. There are 13 cards in each suit. So this will be 13C5. Again, technically, I would take the rest of the cards in the deck. I'd say that 13C5 times that number C0. So 52 minus 13. There are 39 cards left in the deck. I would say 13C5 times 39C0. But 39C0, anything C0, choose 0. That's just 1. So I don't really need to write that. Okay, this is 13 factorial over 5 factorial, and then 13 minus 5 is 8 factorial. Let's do this. 13 factorial over 5 factorial, 8 factorial. So there are 1,287 ways to get 5 diamonds. Now I need to know how many total possible hands are there. Well, there are 52 cards. And you're going to be dealt, choose 5 of them. So this was 52 factorial over 5 factorial. And then 52 minus 5 is 47 factorial. Some big numbers here. 52 factorial divided by 5 factorial, and then 47 factorial. All right, 2,598,960 total possible 5-card hands. So then the probability that you get 5 diamonds is 1,287 divided by 2,598,960. This is about, let's find out, 0.000495. So this is a very, very small chance. All right, we talked about cards. Let's talk about coins. What is the probability that exactly 4 of 5 coins flipped are heads? So exactly 4 out of 5 coins are heads. Well, the first thing we need to do is select 4 of 5 coins to be heads. And we're going to do that over the total number of possibilities. So this is the total number of different flips. I've got 5 coins. I'm going to choose 4 of them. 5, choose 4. This will be 5 factorial over 4 factorial. 5 minus 4 is 1 factorial. All right, 5 factorial, and then 4 factorial there, 1 here. This is 5. There are 5 ways to choose 4 out of 5 coins to be my heads. Now, the total number of possibilities. For the first coin, two things could happen. I could get either heads or tails. For my second coin, two things could happen, heads or tails. For my third coin, oops, I wrote a 3 because I said third. For my third coin, two things could happen. For my fourth and my fifth coin, each of those, two things could happen. So I'm flipping all of them. So this is 2 and so this flipping this coin and this coin and this coin and this coin and this coin. So I'm going to multiply all this together. This is the same as saying 2 to the 5th power. And 2 to the 5th power is 32. So the probability that you get exactly 4 heads is 5 out of 32. Or roughly, 5 divided by 32, 0.15625. This is a little over 15% of the time. What's the probability that you get exactly 5 out of 5 coins? So I'm going to do a very similar process. Instead of selecting 4 of 5, I'm going to select 5 of 5. And again, dividing this by the total number of possibilities. Well, in this case, 5 of 5, that's 5C5. 5 factorial over 5 factorial, 5 minus 5 is a 0 factorial. But I don't really need to do that. I just need to think about it and say, how many ways is there to select 5 objects if there are 5 in total? Well, there's only one way. That's to select all of them. And the total number of possibilities, we've already determined this earlier. 2 to the 5th power is 32. So probability of exactly 5 heads is 1 out of 32. So this is 0.03125. About 3% chance. All right, the last thing we'll do is using combinations and addition. It says here, sometimes counting problems will use the phrases such as at least or at most. These problems will use addition to add the possibilities that satisfy the event. So number 5 says, what is the probability that at least 4 out of 5 coins will be heads? At least 4 out of 5. So the probability of at least 4 of 5 heads, this is going to be equal to the probability of exactly 4 heads plus the probability of exactly 5. So to get at least 4, 4 is the minimum, but you could get more than that. The only possibility more than that is to get all 5? Well, exactly 4, we found that earlier. That is 5 over 32. So this is 5 over 32. And exactly 5, we just found that. This is 1 over 32. Adding those together, I get 6 out of 32. So then the probability of at least 4 out of 5 heads this is 6 over 32. Or roughly 0.1875. I've got 2 more problems here. You roll 3 6-sided dice. We're going to assume these are fair, evenly weighted dice. What is the probability of at least 2 of the dice showing 6? So we want 2 parts here. We want probability here. So the first part is going to be how many ways can I select 2 out of the 3 dice here and have those be 6? At least that. So that's the first part. Let's find that. At least 2 6s. This is going to be equal to exactly 2 6s. Okay, plus exactly 3 6s. Sorry, it says at least 3 6s. So to get exactly 2 6s, I'm going to first choose 2 out of the 3 dice to lock in as a 6. So of the 3, choose 2 of them. Now remember, I've got a third dice. Once I've selected 2 of these 3 to lock in place as 6, how many different things could this third dice be? The third dice could be a 1, it could be a 2, it could be a 3, 4, or a 5. The only thing it can't be is another 6. Because if it were another 6, then I'd be in this territory, exactly 3 6s. So it could be 5 different things. I'm going to take this and multiply by 5. All right, in the calculator, let's go to this, and we'll change these numbers to 3 factorial, then 2 factorial, that's how many I'm choosing to be 6s. 3 minus 2 is 1, so 1 factorial. This is 3. So I'll have 3 times 5, or 15. That's the number of ways to get exactly 2 6s on 3 6-sided dice. To get exactly 3 6s, I'm going to choose 3 from all 3. Well, again, I could take the calculator out and show you, but I could just as easily say there's only one way to do that. I'm selecting all of them to be 6s. Only one way to do that. They're all 6s. So combined, this is 16. 15 ways to get exactly 2, 1 way to get exactly 3 6s. Now I want to divide this because a probability is two parts, the number of ways to satisfy the event, we found that, 16 in total, over the total number of possible rolls for 3 six-sided dice. This will be the total number of possibilities. So for this part, the first dice, I could have 6 things happen. A 1, 2, 3, 4, 5, or 6. And for the second dice that I roll, 6 things could happen. And means multiply. And for the third dice, I could have 6 things happen. So 6 times 6 times 6. This is the same as saying 6 to the third power. 6 to the third power is 216. So then the probability of at least 2 sixes, this is 15 over 216. Which is 0.0694 repeating. I should say about that. So this is almost 7%. I'm sorry, I did 15. We need to do 16. I forgot about the 1 here. Let's redo that. That's 16 divided by 216. Okay, so this is 7%. A little over 7%. So 0.74. Okay, lastly, a teacher has a large database of true-false questions, half of which are true and half of which are false. If the teacher selects 6 questions at random for a quiz, what is the probability that at most 2 questions are true? Okay, so again, 2 parts. We need to find out what are the number of ways to select at most 2 true. So let's do that part first. At most, 2 are true. And then the second thing is we need to know the total number of possibilities. Okay, so at most 2 are true. So that means the highest number that could be true is 2. So I need to find exactly 2, but I could have less than that because it says at most 2. So I could also have one of these questions be true, and I could also have 0. So let's start there. This is going to be equal to exactly 0 true plus exactly 1 true plus exactly 2 true. So this is 6C0. This will be 6C1. Of the 6 questions, I'm choosing 0 of them to be true. Here, of the 6 questions, I'm choosing 1 of them to be true. And technically, I'd say for the other one, what are the other possibilities? Well, for the other possibilities, they're false. There's only one other possibility. So I can multiply by a 1, but I don't necessarily need to. And then here, same thing. 6 of them, C2. Okay. Do this. 6. 0 of those, and 5 remaining here. This is 6. Oh, no. Sorry, this is a 6 here. There's one way to do this, which makes sense. To get exactly 0 true, there's only one way to do that. You get all of them false. Okay, now 6C1. We got 1 here and then a 5 there. This is 6 ways to choose one of them to be true. And let's do a 2 there, and a 4 here. This is 6C2, which is 15. So combined 15 plus 6 is 21 plus 1. This is 22 different ways to get at most 2 true. Now over, we need the total number of possibilities. Well, for the first problem, it could be true or false. So there are 2 possibilities there. For the second problem, 2 possibilities, true or false. For the third problem, true or false, 2 possibilities. Same with the fourth, the fifth, and the sixth. This is 2 to the 6th power. 2 to the 6th power is 64. Which means the probability of at most 2 true is 22 over 64, or roughly 0.34375, so a little over 34% of the time. All right, hopefully this helps give you an idea of the difference between permutations, what we worked on last time, where the order matters, and combinations, where the order doesn't matter. If you have any questions, please let me know.